Hello all. Welcome to another lecture of the regression analysis course. In this video, we will examine the covariance between the estimates of the parameters obtained using the ordinary least squares method. So let's start. Given any simple linear model, that is y is equals to beta naught plus beta 1x plus epsilon, where y is the dependent variable and x is the independent variable. We have model parameters beta naught and beta 1, and epsilon is the error term present in the model. We would have information about the dependent variable and the independent variable, and we use this information to get an estimates of the model parameters. And when we find an estimator of beta naught and beta 1, those estimators are not the true value. The estimates we get changes if we took a different sample. So if we change the dataset, the value of beta naught hat and beta 1 hat would change. And that changing is the uncertainty. And that uncertainty is quantified by variance. Variance of an estimate accounts for how much a single estimate varies across different samples. But then we have another question. How much two estimates beta naught hat and beta 1 hat vary together? And that's where covariance comes in. Covariance between these estimates helps us understand how their estimation errors are related. And this is crucial when we combine them to assess the total uncertainty in predictions. Let's say you are given this sample data, where you are trying to estimate how much students' exam scores depend on how many hours they studied. So we have a dependent variable over here and an independent variable. The dependent variable is the exam score and the independent variable is the study hours. And thus we can create a simple linear regression model y is equals to beta naught plus beta 1x plus epsilon. Given this data set to us, we have the information of the dependent variable for 6 observations. We have exam scores of 6 students and their respective study hours. So we have the values of the study hours for the 6 observation. We have information about the dependent variable y. We have information about the independent variable x. But what we don't know is the value of beta naught and beta 1. So we find an estimator of beta naught and an estimator of beta 1 denoted by beta naught hat and beta 1 hat based on this data set. And we have learned a method called ordinary least square estimation method, using which we can find an estimator of beta 1. Using the formula I have written over here. And this beta 1 hat is computed by using the information given in the data set. Once we have an estimator for beta 1 hat, we can compute an estimator of beta naught hat by using, again, ordinary least square estimation method. And using that, we have that beta naught hat is equals to y bar minus beta 1 hat x bar. This means that an estimate of beta naught hat is dependent on an estimate of beta 1 hat. And this mathematical dependency means that when beta 1 hat varies due to variation in the sample data, it induces variation in beta naught hat. And when we look at our model y is equals to beta naught plus beta 1x plus epsilon, we say that beta naught and beta 1 are conceptually separate parameters, but their estimators are not independent. This is because both estimators are computed from the same data set. So in this exam score example, we have to compute both beta naught hat and beta 1 hat. And to compute both the estimators, we use the same data set. And because both estimators are computed from the same data set, so they are statistically linked and their estimation errors can be correlated. And this correlation is captured by the covariance. And that is why covariance is important, because it helps us understand how their estimation errors are related. Let's start by quickly reviewing the properties of beta hats we have already seen. The first property is that the estimates of the beta parameters obtained using the ordinary least square method are linear combination of yi. The second property we have seen is that all the estimates we have for betas, beta naught hat and beta 1 hat, are unbiased. And in the last video, we discussed about the variance of these estimates. So let's explore what would be the covariance between these estimates. But before we find out what would be the covariance between these estimates, let's see what would be the covariance between the sample mean and beta 1 hat. We have used this result covariance between y bar and beta 1 hat while estimating variance of beta naught hat as well. So let's start. We have to find the covariance between y bar and beta 1 hat. Y bar is the sample mean. Given n values of the dependent variable, y bar is the average of all those n values. That is, y bar is equals to summation yi divided by n, where I goes from 1 to n. And using the first property of beta 1 hat, that beta 1 hat is a linear combination of the observed values, beta 1 hat can be written as summation j going from 1 to n kj yj. Awesome. So this is something we have already seen earlier. Let's try to see how we can simplify it further. For that, we use a property of covariance, which is a bilinearity property that says the covariance between summation AIXI and summation BJYJ is equals to, you pull out summation from both the terms, you pull out AI and BJ, and you get it equals to summation over I, summation over J, AI, BJ, covariance XI, YJ. We use this property and we get that covariance summation yi divided by n, comma, summation kj yj would be equals to, we pull out summation from both the terms and we have summation over I, summation over j of 1 divided by n, because that's the AI we have in the first term, times kj, because kj is the bj we have from the second term. And then we will have covariance of yi, comma, yj. All right. So far we have covariance y bar comma beta 1 hat is equals to summation over I, summation over j of 1 divided by n kj covariance yi comma yj, and we get this using the bilinearity property of covariance. In the next step, we change the order of summation. So we have summation over I and then summation over j in the first line. In the second line now, we have changed the order. So now we have first written summation over j and then summation over I. And all the other terms, we write it as it is. And now if we look at this line, n is the number of observation and the number of observation is going to be a fixed quantity. So we pull out that fixed quantity of both the summation sign and we have 1 divided by n summation over j, summation over I, kj covariance between yi and yj. Awesome. And the next term we have inside the summations is kj. Kj does not depend on I. If you vary I, Kj would not vary. Kj varies as you vary J. So this Kj is a constant with respect to the index I. And you pull this Kj out of this summation over I. And therefore, covariance between y bar and beta 1 hat would become 1 divided by n summation j going from 1 to n kj times summation over I covariance yi comma yj. Perfect. And now let's try to simplify it further. To simplify it further, we use another property of covariance. That is, summation covariance of yi comma yj is equals to variance of yi plus summation I not equals to j covariance of yi comma yj. And when we use this property of covariance over here, we can directly replace this summation over I covariance yi comma yj by this property of covariance. And we would have covariance between y bar comma beta 1 hat is equals to 1 divided by n summation over j of kj times variance of yi plus summation I naught equals to j covariance between yi comma yj, and this we get using the property of covariance. In the next step, we use distributive property for multiplication. So we multiply 1 divided by n summation over jkj with both the terms we have inside the parentheses, and we get this expression. In the next step, we use the fact that because of the assumption on the error term that all EIs are independent, as a consequence, we get all the observed values yi's as also independent. And if all yi's are independent, covariance between yi and yj would be equals to 0. And thus, the second term becomes 0. We directly use the consequence of the assumption that all EIs are IID. And we'll be left with just the first term. That is 1 divided by n summation kj sigma square. In the next step, we use the fact that sigma square is unknown, but it is a fixed quantity. And therefore, we can pull sigma square out of the summation sign. When we do that, we get sigma square divided by n summation over j kj. In particular, for beta 1 hat, we proved that beta 1 hat is equals to summation kj yj. And we further proved two other properties of kj, that is summation kj is equals to 0 and summation kj xj is equals to 1. So here we use the fact that summation kj is equals to 0 and we get covariance between y bar and beta 1 hat is equals to 0. So we have used a lot of properties of covariance in obtaining this value. And now in this video, we are going to use it to obtain the covariance between the estimates beta 1 hat and beta naught hat. Let's find the covariance between the estimates beta 1 hat and beta naught hat. We first plug in beta naught hat is equals to y bar minus beta 1 hat x bar because that's the ordinary least square estimate of beta naught hat. It is dependent on sample mean and beta 1 hat. So we just plug in beta naught hat is equals to y bar minus beta 1 hat x bar. And then we use the property I have stated over here, that is covariance of x plus y comma z is equals to covariance of x comma z plus covariance of y comma z. When we use this property, we get covariance of beta naught hat comma beta 1 hat is equals to covariance between y bar comma beta 1 hat minus covariance between beta 1 hat x bar comma beta 1 hat. In the next step, we use another property of covariance, that is covariance of a comma x comma z is equals to a times covariance of x comma z. And if we look at the second term over here, it is covariance beta 1 hat x bar comma beta 1 hat, and this x bar we have over here is the mean of n values of independent variable. This x bar is a fixed quantity, and since it is a fixed quantity, it is a constant, we can pull it out using this property of covariance. So the first term we would write it as it is, and the second term is x bar covariance beta 1 hat comma beta 1 hat. In the next step, we would use another property of covariance, that is, if you find the covariance of a random variable with itself, you get variance of that random variable. So we use that property and we have covariance of beta naught hat comma beta 1 hat. The first term we have is covariance of y bar comma beta 1 hat, and we have just now proved that the covariance between y bar and beta 1 hat is equals to 0. And then we have the second term minus x bar, which we would write as it is, and then we have covariance of beta 1 hat comma beta 1 hat, which is further equals to variance of beta 1 hat. And we have already estimated variance of beta 1 hat, which is equals to sigma square divided by sxx. And thus we have proved that the covariance between an estimates of beta naught and beta 1 obtained using ordinary least square estimation method is equals to negative x bar times sigma square divided by sxx, which means that if the slope estimate increases due to sample variability, the intercept tends to decrease because of the negative sign and vice versa.